So you are able to run the couplings yourself? No?
Yeah, for the same model that you got it to run for as well.
On the NERSC or on the
HPC. Or
okay.
The USD HPC. I tried to run it for the model that doesn't have the bond between them, I think. It does the overlap code. It's just not updating the way it cars. So I was going to play around with that.
But you do have password for your account for NERSC.
Right? Yeah, I was going to copy him over there to see if that magically changed anything.
But with the couplings that you have by now, you can generate sufficient data for the conference, right?
Mm-hmm. Yeah, I should be able to.
Right.
Hello. You missed lab yesterday.
I didn't know about it when I was home, and I have many classes at 7, so.
What classes?
We have my wife and I have Dawn, so his obedience class.
Oh boy.
Fun.
What?
Nothing.
Oh, you missed it.
No, there. Did you see me?
Oh, alright. Probably.
What's that?
I was pretty sleepy.
Okay.
Oh. I would have believed you. You could have rolled with it. Oh, my phone's in my bag.
Ah, everyone is here. That's great. Today, the first time I will do complete improvisation. I didn't write down the notes. So it will be dramatic change in quality. I don't know, up or down. So, you are welcome to join meeting number 8 in Quantum Chemistry 2, which is a code CHEM767 at the North Dakota State University, allowed for departments of chemistry, biochemistry, physics, M&T program, and so forth. We are continuing, or we are starting new chapter, perturbation theory, that we slowly started last meeting. Oh, everyone gets generous credit for presenting. You are on a good track. If you do not fail, you are on the right path to highest grade. So, before we go to scientific part, there are some administrative stuff. When the weeks are not cancelled, and a couple of weeks will be cancelled because of conferences, some of you are going to them, then we will try to do relatively brief informal lab with the support to this course at Wednesday night in the barbecue room 132. I know one needs to pronounce it QBB or BBQ.
BBQ.
BBQ is better.
Yeah.
Some Quentin Burdock, some beauty. Yeah, but it's easier to remember BBQ. So yesterday we slowly started gathering after 6, and the whole meeting went maybe for half an hour. So it was not. I hope it was not very exhaustive. Handouts. You may decide that you do not believe me, and some of us are visiting medical doctors, do not believe them, and search for second opinion. Here is your option for second opinion from 3 different sources. So one source is CHEM767, so it is standard text half century ago in quantum theory. So most of modern scientists were educating themselves based on this book. The second handout is from Nobel Prize holder Kontanuji, who is working in physics and more specifically in optics spectroscopy. And you will see that this point of view affects the style of narration. And you do not need to read anything. This is just an option. Your time is extremely precious and busy, and you have more pleasant and important things to do. And the third one is by Ira Levine, which is graduate text in quantum for chemists. If you are in chemistry, you may wish to believe the third source at most. Although the result should not depend on source where you borrow it, because it's all well derived. So what else? Done with labs, handouts, homeworks. Pleasant entertainment. So when we met in the lab, you have worked with MATLAB code that mimics, not mimics, exactly addresses the solution for 2x2 two-level system that is perturbed by off-diagonal perturbation, right? And you have got you compared the exact solution with perturbation theory solution of the zeroth order, first order, second order, and thanks to DeYoung, third order. In the lab, your unperturbed Hamiltonian was a diagonal, and the perturbation was off-diagonal. So how do we entertain ourselves during the weekend? Let's cross it out and do diagonal perturbation. Plug it in and see what happens. And add some very brief analysis. For example, I need to admit my own error that you may have not noticed. In class and in the code I lied, but now since I'm correcting it, it is okay. The expression for the first order perturbation is contributed only by the diagonal matrix elements. And in the code, it uses off-diagonal. So basically, for the off-diagonal perturbation, the first order correction is 0. Therefore, one needs to go immediately to the second order correction. While for this stuff, for the homework, the first order will be important, and second order, where you have transition from one level to another, will be less important. But in general, as you ascend in higher rank, in higher orders, it should converge. So just run the code, make screenshots, and write a brief composition of maybe a paragraph. What do you think on this subject? Okay? No objections? Due in 5 days from now in class on Tuesday. Expected time investment, maybe 10 minutes. Okay, so we are done with labs, handouts, and homeworks.
So I missed what the assignment is. I missed what the assignment is. So the current code has a off-diagonal perturbation.
If you look at the first 10 lines of the code, it will explicitly write down the unperturbed Hamiltonian and perturbation in form of matrix, where it has 0 on the diagonal and non-zero on the off-diagonal.
Yeah.
The assignment is to replace this perturbation into such one, where the perturbation is contributing only to the diagonal, where the perturbation affects the energies of orbitals and doesn't induce transition between them. Just check what happens as a exercise in curiosity. Difference of diagonal versus of perturbation to level system. Okay? So who we are and what we are doing? It is a little harder question to identify. So we are trying to dig down to get more specific knowledge in quantum chemistry and get additional chapters that would allow us to do research, competitive research and competitive applications, even in the absence of computers and modeling tools. So by now, most of us are involved in, exposed to computational chemistry, and we know which way to go to complement experimental research with computational stuff. But if it is pen and paper, pure theory, it is a little more arsenal is needed. And we are going through chapter by chapter little additions that would make us able to put this component into a research paper. And research papers is something what you are hunting because you are in grade pro. Okay, at least we are clear with motivation. Dibbler's cartoons. Dibbler? The one you were showing. Series.
Oh, yeah.
Dilbert. I remember one that my office mate kept on his table when I was a postdoc. It was there is a bald guy with very few hairs that plays a boss.
Wally. Oh, no. The boss is the one that has the symmetric hair that sticks out. Oh, okay, yeah.
And there is three cartoons. One this way, another one with arrow down, another with arrow up, and then the person himself with some other people around. First one, our sales fall down like rock, but they need to go up like a rocket. Third one, I'm done with visual leadership. The rest is your problem. So, we are done with motivation. So, perturbation theory is needed when? When the basis is big, or when our resources are limited, and when we want to avoid when exact solution is either impossible or too expensive to pursue, even numerical exact solution. If you want to avoid numerical diagonalization of matrix or numerical solution of self-consistent equations. So it is the cheapest way to approach answer that is ever possible. So then the idea is, which example did you mention yesterday in the lab? For example, you have transition metal ion alone in the vacuum, and then you have with some appropriate positive charge. And then you have negative counter ions slowly approaching it from 6 sides from infinity. And when this negative charge approach it, the energy levels of these d orbitals start to split. One of the ways to predict how they would split is to find matrix elements how the electrostatic interaction affects these d distributed shapes, and instead of diagonalizing the whole matrix, just apply perturbation theory and get the split corrections to energies of these d orbitals. There are many other examples. It is the list of problems where perturbation theory can be applied is much longer than the list of exactly solvable problems. And there are at least 3 sorts of perturbation theory, 2 of which we will cover in this chapter 2 and the third in separate chapter. So first 2 sorts are non-degenerate and degenerate levels. If the energies of states that are being perturbed have different energy, it is one brand of theory. If they are degenerate, like for d orbitals, there are some additions to the theory. And the third thing, when our perturbation is not static but time dependent. So it will be formulated a little bit differently than what we have been doing. So the main idea is that we do have Hamiltonian as unperturbed plus small perturbation. We do have transition from imaginary worlds to a real world in form of lambda-parameter, which changes from 0 to 1. So 1 means real world when the perturbation is enabled, and 0 is auxiliary universe where we do not have perturbation. And the main idea is that if the Hamiltonian is perturbed by this small perturbation, then the exact energy and exact wave function can be written as a power series in powers of this lambda parameter. Zeroth order, first order, same for the wave function. Zero squared. First order. Let's do first. We know for sure two things. First, that if we plug in exact wave function into complete Hamiltonian, then we will get exact energies. So it is our ideal situation in real world that we would like to compute with precise methods if they are available. So this series serves as an approximation for this solution. Another thing that we know for sure, that if you take unperturbed Hamiltonian and plug in the unperturbed wave functions, then we'll get unperturbed energies. So it is something that we know before the solution. What is our technical goal? So we will do some algebraic manipulations that will give us exact expressions for E n first order equals something, E n second order equals something, psi n first order equals something, psi n second order equals something. So as soon as we get these corrections, our task will be complete, will be done. When we were in the lab yesterday, we already took this, at least these two answers. And if you are impatient, you can either flip through pages of these handouts, or you can just go to Wikipedia. It has very adequate representation of the theory. Wikipedia page, perturbation theory in quantum mechanics. How do we get the answer? What is our plan? Please suggest something.
Perturbation theory.
Absolutely right.
Yes.
So, agreed on perturbation theory. How do we derive perturbation theory? Like, let's think as programmers or as administrators. Like, we'll hire mathematicians to work for us. But what is the assignment? What is the task? What should we do? Like, if we have this four, oh, actually 5, 1, 2, 3, 4, 5 equations as input, and this 4 or more equations as output. What should we do to get this circle out of these 5 equations?
Don't you already have one of the answers?
Huh?
You have one of the answers.
Yes, but how do we continue?
We need to approximate that up to 2 terms or 3 terms.
That's absolutely correct, but give us a recipe, a prescription. What should we do?
Take the unperturbed wave function, figure out a means to get perturbed wave function using
Normalization.
Find an
Oh.
perturbed wave function
Yeah,
first.
3 and then
So how would we go?
normalization.
Huh?
no, plug in 3.
No, we haven't done normalization yet.
We'll do it later.
Now we are in trees.
So, here is the same ideology, same paradigm as one does in quantum theory and more generally in math and differential equations all the time. So it's very general idea, not only for here. We assume functional form of the solution and then plug it into the equations that it should serve to. Upon plugging in, we solve for coefficients. So now this is functional solution. It is a summation of lambda to power n with coefficients e, oh, let's do it different, k, k. Right? So lambda is a function, energy is expansion coefficient. So we plug in this functional form and then search for expansion coefficients. Same here. It is summation k, lambda k, psi k, extent. So we need to take these two equations and plug them into exact Schrödinger equation. So we will plug in the series for wave function, series for energies, and perturbed Hamiltonian for Hamiltonian. Series for wave function, series for energies, and use perturbed Hamiltonian. So we plug into Schrödinger equation. Good? So it is our first step. And second step is very standard in quantum theory, and we've done it many times. So the equation will contain wave functions, which are functions, which depend on many degrees of freedom. 2 in the simplest case and infinite in most of cases. We will need to get rid of this basis functions in form of lambda, and we also, in our expression, we will need to get rid of the wave functions if you want to find for energy. So we will need to multiply the resulting expression by the bra from the left, so that all wave functions convolute and disappear. So also all the functions bra from left. And another thing that is natural, but let me pronounce it ahead of time. We will need to agree that 2 series are equal if the coefficients by the same functions are equal. Like if you have a times lambda to the power k equals b times power k, it is equivalent to say that a equals b. Okay? This took me, I was hating this logical step in my undergraduates. If you agree with this, I'm happy for you. This is simple, but a little counterintuitive. So here's our plan. Now we are done as thinkers. Now we need to hire a mathematician, or call him a mathematician inside us. So, Schrödinger equation will consist of Hamiltonian, will consist of wave function, then it will be eigen energy, and then will be wave function again, right? I didn't check myself, but by browsing through this literature on the first source, the Schiff, it makes reference to Schrödinger paper in 1929, so like 2-3 years after developing the equation. So the theory is not very recent. It was considered as an application for quantum theory almost immediately after design of quantum mechanics. Okay, so there are only 4 terms and 6 participants. We like to put in first term. It will be more fun. Just for Hamiltonian.
Just.
For Hamiltonian, only, yeah, the first bracket. H0 plus H prime. And lambda coefficient in front. No. Lambda in front. Enough. Thank you. You did great. Yeah. Sam, would you like to contribute to mathematical derivations? So,
Sorry.
here you put brackets, here another bracket. Will you put an approximate expression for the wave function? Yes, excellent. And another one more term. Yeah. Excellent. Yeah. Many thanks. Let's put the energies. Very good, thank you. Which approach, which will be? It's fine. It's fine. I will put it anyway in the old-fashioned style. E0 t plus lambda e first order. We use letter n, right? Plus lambda squared e second order. And
oh, I'll do that one.
Please. Yeah. Sorry, Aaron. It's a tough competition.
Oh,
You already have it.
don't look at that.
But now we can trim the recording and show only Brandon writing this down.
There we go.
And then show the answer. Yes, thank you for formulating perturbation theory, Brandon. Yes! So, what do we do next? Huh?
Oh wait, distribute.
Yeah, just open brackets. Maybe call it distribute or distribute. How would you pronounce it?
I said distribute.
What do you say? Distribute.
Distribute or distribute?
Distribute sounds better, probably.
I don't know. To me, that sounds like delivering packages.
Like would you say distribution?
Okay.
No, it's
So-
CRI.
I say
Okay, open
distribute.
brackets.
Okay.
Yes, we got the easy jobs.
It's the hardest one.
That's what I
Yes.
said. We.
Yeah. Okay. So how many terms will be on the left side?
6.
So it will be 6, and how many terms on the right side?
9.
If we keep only up to second order. 3 by 3, 9. So see, graded course is something advanced. Okay. H0 psi 0 m plus H0. Oh, I have an algorithm. I will repeat this same, but putting h0 in front of each. h0 lambda psi n first order plus h0 lambda square psi second order n. Okay. Now I'm putting lambda h prime and then repeating the same thing. Psi n 0. H prime lambda h prime psi 1 n plus lambda h prime lambda squared psi second order n. I have a plan. There will be total 9 terms. I do 3 first and then ask for help for another 6. There are 2 persons who didn't try to do that. So I'm taking the first term in this bracket and then repeating all terms in the second bracket. So E sub superscript 0 sub n times psi 0 order n plus E 0 order n lambda psi first order n plus E 0 order n lambda squared second order n. Would you like to plug in some one square here? And let's look onto the original expression. Was there any additional powers of lambda? Lambda, here it will be, for the term number 5, it will be lambda squared, right? So what you are doing, you are multiplying lambda times epsilon times lambda times psi.
Square, that's what it became.
Okay, perfect. Thank you very much. It is very hard. Without your help, we will not survive. There will appear up to 4th power of lambda. So second order correction to energy times lambda cubed times
Psi
first order correction to the wave function. Perfect. Many thanks. Everyone follows, right? So we plugged in our series expansion into exact Schrödinger equation. What is our, so we are done with this step. So this convolution, we will postpone it for later. Let's do it for the third step. Breaking this big equation onto a set of several shorter equations. Because we are so tired to write this long equation. It was almost impossible for one person. Thank you much for that. So, how do you break it onto several parts? If you consider left and right part as a Taylor series, right? Summation lambda to the power k and some coefficients k sub k. Summation lambda power k b sub k. Right? This will mean that b0 equals a0, a1 equals b1, a2 equals b2. So the coefficient in front of specific power on the left side should be equal to coefficient in front of the same power on the right side. I know, just for most people it is self-evident, but we better pronounce it. Coefficient coefficient in front of given power of lambda equals to coefficient in front of the same power on the right. I'm going to erase it and start splitting big equation onto several equations that will look this way. So, zeroth power. Why should I write everything if I have so bright helpers? So please underline the terms that contain lambda in power 0. Only underline in the long equation.
Oh, okay, in this side, this one should be. Oh, yeah.
Okay, and
This
on
is
the
going to this one there.
and on the left side.
Here.
Okay, so with precision up to 0th order,
Yeah, zero.
perturbation theory is reads H0.
There's a power of lambda missing in one term. Where? The left hand side, on the bottom in the middle.
Which one is missing?
Where?
In the left hand side, in the middle on the bottom. Yeah,
Here?
see that's square,
Here.
lambda square.
Let's double check. Let's double check.
Then
So,
yeah.
so here we do this one, yes, and this one should be cube, right?
Well, you have
Well,
a lambda.
there's one in front.
Okay,
So
you can raise this one. Okay, so it is Jabot's perturbation theory, 0th order. Thank you, Sam, for volunteering.
Exact solution, isn't it?
No, but then you have to.
So please underline,
Yeah.
first underline
That's the exact solution.
those
Zero
terms
perturbations.
that
There are no
contain only
perturbations.
first power of
That's the
lambda.
exact solution. Yeah, of the real system. Correct. You go to that. You solved it.
That's it on the left and on the right.
Right.
That's it. So H0 times psi first order sub n, first order, plus H prime times psi 0th order sub n equals E energy first 0th order sub n times psi first order sub n first order sub n plus energy first order times psi zeroth order sub n. Many thanks. Perfect. Let's go. Squared, lambda squared. Oh, so it's matrix style of analysis. We just take the anti-diagonal. Good, good. Unperturbed Hamiltonian times second correction to wave function plus perturbed Hamiltonian times first correction to wave function equals to second order to energy times unperturbed wave function plus first correction to energy times first correction to wave function plus zeroth order energy times second order correction for wave function. Excellent. Many things. We are not going to the next orders.
The next order is good. Decrease.
We cannot go to next orders with this formulation because some of the third order terms are already missed. We need to plug in higher order series, about twice as longer series to get answers for.
Let's not do that.
To get order n, you need to start with series of the length 2n, something like this. Whew. We are not done. We achieved an important level. But we have Jabot-Sam-Levy perturbation theory. But right now, they are just expansion coefficients in front of lambda, in front of these powers in lambda coefficient. But we need corrections. We need to find for e to the superscript 1, e superscript 2, and then we also need to find psi superscript 1, psi superscript 2, right? Of course, we will go here. We need nothing. First, zeroth order is already solved. But for the first order corrections to both energy and wave function, we need to practice convolution of the wave function. You can consider this one is ket. And we are going to convolute it with bra, right? And we do have previous experience that when you convolute ket and bra, you are getting either 0 or 1 because of orthogonality relationship. So we suspect orthogonality, or we seek for orthogonality, right? But do we have it? Do we have orthogonality or orthonormality for corrections? Not for the wave function, but for the correction. No one promised us. There were no theorems telling about orthonormality relations for wave functions. So our typical trick of convoluting bra and ket from left and right may fail if we do not take measures ahead of time. So we need to take measures and consider whether we have orthogonality or something instead of. How do we deal with it? There is the same philosophy as we used here. So we took equation that we know for sure, Schrödinger equation, and we plugged in our series for wave function and for energies. Why don't we take an equation for orthogonality for exact wave function that we know for sure and plug in our series? I think we will not violate any rules. We just reshuffling whatever we already have on the board. So, what if we assume that our Schrödinger equation with complete Hamiltonian provides good wave functions that are orthogonal, then we can take it as a starting point. So if we do have psi m of the complete exact solution without any singles here, and psi n equals delta function m n. Right? And now let's keep psi sub m as an exact wave function, and instead of psi sub n, we will plug the series and just explore what will happen. Make sense? And this Bryant cat, it means that we integrate over dx, or how many variables we have, psi star m of all variables times psi sub m of all variables, right? So psi m vertical psi m equals psi m, and here we are writing psi zeroth order m plus lambda times psi first order plus lambda squared this should be equals to do you like it, or just too boring? I think we need to increase the level of entertainment. Probably plug in the series on the left side as well. Right? Otherwise, it's not as interesting. We need the orthogonality relations or replacement of rules of involution for Bryant cat for the corrections. Here we can solve it. We can get something for convolution of the corrections and the complete wave function. That from here we will get psi m to psi 0 sub m equals delta mn, and from this one we will get psi m psi n first order equals 0. because we have lambda to power 0 here, plus lambda times first times 0, so expansion coefficients in front of other lambdas are 0. You can consider the right side as a series in lambda. So what I'm going to do right now is to plug in series for the left, for the bra as well, make little conclusions out of it, and we will be done. I know that some of you have tough schedules, and you may leave if you need time for transit. So there will be maybe one line more in our case. So what I'm going to do is to make screenshot of the board number 1, then erase it, and then write one line there. So when we meet next time, the first thing we will do, as already, we will reproduce these 3 equations, and we will go from there. So once again, psi m equals psi is lambda psi m over 1 plus lambda square psi second power times psi m over 0 plus lambda psi m power plus first order correction, lambda 2 second order correction for the coefficient n. Then this one will be equal lambda to the 0th order, 0th power, psi m 0th, psi n 0th, plus lambda to the first power, psi m first order times psi n 0th order plus psi m 0th order times psi n first order plus lambda second power psi m 0th order times psi n second bracket plus psi m first order times psi n first order. This was this. You have more terms? Yes, no? Should be symmetric. 0, 2, 1, 1, and should be 2, 0. Psi m second order, psi m 0th order. Which will be This one and this one, contributing to the power 2. Now, what is it equal to? It is equal to delta mn times lambda to 0th order plus 0 times lambda to the 1st order plus lambda square times 0. 0 times lambda 2nd order. Make sense? Or it is a little puzzling? Same thing as you did on the other board. We have an expression that we know for sure. Psi n exactly equals delta m n. Delta function, which is 1 or 0. Now, let's consider left and right part as power series. So left part appears by product of power series for bra and for cat. And after doing the algebra, we can combine terms that stand as factors in front of 0th, 1st, and 2nd order of parameter lambda. Good? Raise hands if you do disagree. And then the right side, it is just delta mn, just delta function. But let's jump out of box and consider it as delta mn being a coefficient in front of lambda to power 0s, which equals 1. Then 0 as a coefficient in front of power 1, and 0 as coefficient in front of power 2. Then this big equation can be also decomposed on a set of shorter equations. Set decompose set of shorter equations. So for power 0, we are writing that psi 0 m psi 0 n equals delta m. No wonder. We agree with it even before we started. 0th order, unperturbed Hamiltonian, orthogonal. Now for the 1st order. On the left side, we have psi m 1st order times psi n 0th order plus psi m 0th order times psi n 1st order equals what? Coefficient in, we do not have on the right side, the coefficient in front of the 1st power is 0. Therefore, we set up this stuff, which is in fact p is a coefficient in front of 1st power, to be equal to 0. And then we can also make the same trick for the second order. So it is also will be 0 on the right, and on the left it will be psi 0 m psi n 2 plus psi m 1st psi n 1st plus psi 2nd m psi n 0s equals 0. So these relations will serve as a rules to perform the trick with convolution. If we look on the equations there that contain wave functions, and we want, or corrections to wave functions, and we want to get rid of them, remove wave functions, we will start with corrections to energies. And in order to remove wave functions, we will multiply everything by bra from the left, and follow these prescriptions with the purpose to remove wave functions and their corrections completely. Okay? So we will take the zeros, first and second order expressions derived by Jabet, Sam, and Levi, and multiply them by graph from the left and process them according to this expression, to these three rules, these three expressions. And hopefully we will get the same expressions, same answers as we practiced in the lab last night. I think we have this room reserved, but I think intellectually it is sufficient to digest and prepare and be fresh next time. So let me announce meeting number 8 complete. Thank you for joining. We are going off record. I will stay here just in case someone has more questions.
We get done right at 1. So now we're lunch, rush, and now all the food should be fresh, right? So if we go at 11, I don't know, food is.
So you're gonna give me your receipt?